Welcome to the exercises for chapter 13. This chapter is all about confidence intervals, how to compute them analytically and also empirically using bootstrapping, how to interpret them. Lots of things about confidence intervals. Let's begin with exercise 1. Here, we are going to explore the relationship between confidence intervals, sample size, and standard deviation. Now, at the beginning of this chapter, I discussed the relationship between confidence intervals and standard deviations and how those two quantities share some conceptual overlap, but they are mostly distinct. But the confidence interval computation does include the standard deviation, the sample standard deviation, and the sample size. So the purpose of this exercise is basically to produce this figure and then interpret it. So what are we looking at here? So here we are looking at the relationship between the width of the confidence interval. So that's the distance between the lower confidence interval bound and the upper confidence interval bound as a function of the standard deviation and the sample size. Now you are going to use the analytic formula. I'll show you that formula in a moment to implement this exercise, which means you don't actually need any data. You do not need data to perform this exercise. Okay, so you implement the equation that I showed. You vary the sample standard deviations from 0.1 to 7, and the sample sizes from 50 to 1,000. Okay, so I will scroll up. I'll show you this formula. Then I'll switch to the code, and then I will have a few remarks about this, interpreting this result here. So here is the formula for a confidence interval. So we have the sample mean, and then we have the sample standard deviation and the square root of the sample size. And this t star sub k here corresponds to the t value in the t distribution that maps onto whatever confidence interval you're looking for. So if we want the 95% confidence interval, which is what most people usually use, then this would be whatever is the t value corresponding to 0.95 with k degrees of freedom. And of course, you want to make this two-tailed because this is plus or minus the confidence interval around the mean. Now, for this exercise, we don't care about the mean. So you can just set this implicitly to 0. It makes things a little bit easier. You manipulate in a double for loop. You will manipulate s and you will manipulate n, and t. So the value of t is going to change based on the number of degrees of freedom, which comes from the sample size, but you want this to correspond to a two-tailed test for 95% confidence interval. Okay, so now let me switch to code and I'll show you the implementation. So here I have the range of sample sizes and standard deviations. This is initializing the results to the confidence intervals, and I guess technically it's the confidence interval range that we want, not the interval itself. But you can see that it's going to be a matrix of sample sizes by standard deviations. So here I have a double for loop, and inside this loop, I define, here's the standard error of the mean. So that's that's that other term to the right in the formula. So the sample standard deviation divided by the square root of n. And here I'm using the stats.t.interval function to compute the confidence interval for me. I want a 95% confidence interval with n minus 1 degrees of freedom. Of course, this will vary with sample size. And yeah, I mean, here I'm just specifying x bar, the sample mean, to be 0 because it doesn't actually matter. And then this is just a trick here. So thing is, this is going to return a confidence interval bound, but because the average is 0, and because this is the analytic formula, this function is implementing the analytic formula, it's guaranteed to be symmetric. So instead of taking the difference between the lower bound and the upper bound, we can just take the positive value, the upper bound, and double it. That's going to give us the range. Just a little bit of a shortcut. Okay, so then, well, the rest of this is not so interesting. It's just visualizing this image with some modifications. Okay, so what do we see here? How do we interpret this? So first of all, remember that every single point here, every element in this matrix, corresponds to the 95% confidence interval. So the confidence interval is exactly the same But the smaller the confidence interval, so the narrower the confidence interval, the more precision we have, the more confident we can be about the possible range of values of the population parameter. So we're always going to be 95% confident about our estimate of the population mean, but that confidence, our amount of confidence, is going to be very wide for large standard deviations and small sample sizes, and our 95% confidence is going to be very narrow when we have smaller standard deviations and larger sample sizes. Here we are in exercise 2 of chapter 13. This exercise goes in conjunction with the next several exercises up to exercise 6 in this chapter. So, if possible, you define your own schedule, but if possible, I do recommend sitting down for a block of time to try to do all 5 of these exercises. So, exercise 2 up through exercise 6, all in one setting because they're all closely related to each other. Okay, so what you want to do here is create a population of data. So we are basically just going to generate a bunch of random data, but we are going to consider that to be our absolute full population that we are interested in. And the reason why we are doing that is so that we have the true population parameters. We can know the true population mean, the true population standard deviation or variance, any characteristic that you want. You know the absolute true value, the ground truth of that population, because we are simulating the population. And then we're going to sample from that population and see how these sample characteristics and, of course, the confidence intervals relates to the true known population parameters. That's a great advantage of simulating data and learning about statistics by simulating data because, in practice, you rarely have access to the full population. Okay, so the full population is going to be 10 to the 7 numbers drawn at random from a normal distribution with a mean of 0 and a standard and a variance of 4. So that is our true population. Now, this population is not going to have a mean of exactly 0 because we're actually creating this distribution in, the way we are generating this is as a very large sample from a theoretical distribution, but we are going to treat this as our true empirical population. Then you want to just make a histogram of these data, visualize the data in a couple of different ways. I don't have that figure in the book, but I'll show you in the code. Okay, so then you want to draw a random sample of 500. So 500 data points randomly sampled from our population. Compute the 95% confidence interval around the mean and visualize the results. And you can show that in a figure like this. So here we see in light gray, this is the sample histogram. So it's not the histogram of the full population, it's the histogram of the sample data. Here we have the sample mean in dashed line here, and then the 95% confidence interval as this darker gray box that's drawn around it. And then we have the population mean in as this dotted line here. Now, what you can also do is zoom in here. So this is zoomed all the way out, -15 to +15. But if you zoom in to, maybe -2 to +2, that will help you see the relationship between these a little bit better. And what we see in this exercise is that or certainly in this particular run, that the true population mean does lie within the 95% confidence interval around the sample mean. Okay, so that is this exercise. I'll now switch to code and show you my solution, and then we'll continue on to the next exercises from there. So here is the population size, the size of the total population. Here is where I draw the data to create this population. Now, it might look a little weird that I have these data to the power of 1. Why even have this in here? But that is actually for later exercises. So we're going to square these data. We're going to generate a different population, but that's going to be for later exercise. So for now, just ignore this strange looking little piece of useless code. Okay, so here is the exact population mean. Now, of course, we expect this mean to be close to 0, but it's not going to be exactly 0 but this is the true population mean that we can compare against our sample mean and confidence interval. So here is some visualization. I didn't include this figure in the book chapter, but it's always a good idea to visualize data whenever you can and however you can. Okay, so here I'm just plotting some data points from this population. Now, the thing is, this is a huge population of data. There's lots and lots of data here. So just plotting every single data point is not very practical. It's going to take Matplotlib a really long time to generate the plot. It's just going to be very loud and noisy. So instead, what I'm doing is just plotting every 1,000th sample. So it's just a way to visualize the raw data without visualizing all of the data. You can also, there's other ways you could do this. You could sample, let's say, pick 10,000 data points completely at random and plot those. Lots of different ways that you can visualize raw data like this. All right, so here we see some random data and the distribution. This is absolutely beautiful. This is an amazingly perfect normal distribution. It looks really great, and that's because we have such a ginormous sample size. We have a really big population size. Okay, now what we do is draw a random sample. So I'm going to choose randomly from this population 500 data points at random. So we have our population, and now we do some experiment. We collect some data, and these are the samples that we happen to collect. So now we can compute the mean and the standard deviation of this particular sample. Now, of course, we expect that this should be pretty close to the population mean, but there's no guarantee that this is going to be very, very close to the population mean. It's just something we expect because we are sampling at random. Okay, so then again, I use this stats.t.interval function to compute the analytic standard confidence interval for 95% confidence. Here I'm just showing, if you compute or parameterize the confidence interval as a percent, you have to divide by 100, so it inputs as a proportion. Just a little thing to keep in mind. Here we have the degrees of freedom, so n-1. The location, the center of the confidence interval is the sample mean, not the population mean, the sample mean. And the scale is or the standard error of the mean is the sample standard deviation divided by the square root of the sample size. Okay, so let's see. Then the rest of this code is just some, Matplotlib housekeeping to generate this function, this figure. So what I want to do now is actually first just comment that the histogram of the data, so the distribution of the data, is way, way, way bigger than the confidence interval itself. So the confidence interval is narrow, whereas the data can be much more widely dispersed. Okay, I'm going to uncomment this line here. You can see that's just changing the x-axis limit. So instead of seeing all of the sample data, we're just zooming in a little bit here just so we can focus in on this region. So yeah, here we have the sample mean and the population mean. You can see they're both fairly close to 0, but if you would zoom in even more, or just print out the population mean, I think you would see that it's not exactly 0. It's just very close to 0. So I'm going to just run this a bunch of times. Now, in principle, if I run this 20 times, this is a 95% confidence interval. This worked out beautifully. I expect that in 5% of cases, approximately over, if I repeat this code and draw new samples many, 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 many times, I expect that around 5% of those times, and I happen to get lucky here, getting it on like the third or fourth hit, the population mean is going to lie outside of the confidence interval of the sample mean. So here you see the sample mean was like, 0.32 or whatever this number is. And the 95% confidence interval is here. It's outside of the population mean. So we know that, this is wrong. This is a statistical fluke. In fact, if we were performing statistical inference here, based on this confidence interval, we would come to the conclusion that these sample data were not drawn from this population with this population mean, because we would come to the conclusion that using a alpha threshold of 5%, we can say that this sample has a statistically significantly different mean from the population mean. That is a completely valid statistical conclusion, but is completely wrong. It's a statistical fluke. It's an alpha error, type 1 error. We are claiming to have a statistically significant difference or effect when there is no effect there. So, this happens. This is how it goes in statistics. It happens in real data as well. The thing is, now in simulated data, we know that this is a statistical fluke. In real data, you don't know that this is a statistical fluke. So what can you do? Well, you can try to draw larger samples. You can try to do independent replications. You can do subsequent analyses. So there's lots of things you can do in real data. But the truth is, this sort of thing happens in literature, in science. It gets published and incorporated into part of human knowledge. And so, the best we can do as scientists is to trust findings that are reproduced by multiple different experiments, multiple different research groups, and trust the long-term process of science and not put too much faith into any one individual finding because of the risk of situations like this. Here's the video for exercise 3 of chapter 13. As I mentioned in the beginning of the previous video, this exercise and also the next few exercises follows directly from the previous exercise, exercise 2, using basically the same code, same principles, same concepts. So if you haven't done exercise 2, make sure you go through that one first. Okay, so at the end of the previous video, I showed you that purely by chance, we ended up getting a random sample drawn from a known population where the population mean was outside the bounds of the sample mean. So that was a statistical fluke. It shouldn't happen. But because we have a 95% confidence interval and not a 100% confidence interval, then, that sort of thing can happen. Okay, but how often does it really happen? Is it actually happening on 95% of samples just because we specify a 95% confidence interval? So the question is the confidence interval really veridical? Is it really descriptive of what happens with future samples? So that is the question we will answer with exercise 3. So basically what you want to do is take the same population and the same code from exercise 2, but now repeat that code 5,000 times. So in exercise 2, we drew one sample, we computed the 95% confidence interval, and now we did that once. So now here in exercise 3, you want to do that 5,000 times. So 5,000 random, unique, distinct samples of n equals 500, compute the 95% confidence interval, and then calculate whether the true population mean is within that confidence interval bound. So you'll have to add a little bit of extra code for that because in the previous exercise, I just did it qualitatively, right? We just looked at the graph and just visually noticed whether the population mean was inside or outside the confidence interval. Now you need to calculate this for each of these 5,000 random samples, so 5,000 iterations. And then just compute the average of all 5,000 runs. So you want to know how often over these 5,000 random samples, these 5,000 iterations, how many times was the population mean within the 95% confidence interval? Now, it should be somewhere pretty close to 95%. Okay, so now I'll switch to code and I'll show you my solution and have a little bit of a discussion. So here is the code or the for loop that runs this experiment. You will see a lot of this code is the same as the code for the previous exercise. In fact, this is basically literally just copy pasted. I don't even know if I changed anything from here. But there's a little bit of new code here. So I'm running 5,000 experiments. This is soft coded here because in the next exercise, we're going to change this sample size. Okay, so then here is, the important addition here. I say if the population mean is greater than the lower bound and it's also less than the upper bound, then I'm going to set this element inside this vector to be 1, and otherwise it's initialized to be zeros. So then at the end, I just need to compute the average of all of the of this entire variable. Okay, so we run this, and for a 95% confidence interval, we find that a little bit less than 95% of the time, the the true population mean was contained within the bounds of the sample confidence interval. So we can rerun this multiple times, and you'll always find it's going to be somewhere around 95%. So sometimes a little bit below 95%. Here it was a little bit above 95%. Of course, we're dealing with random numbers here, random samples, so and a finite number. So we expect this to be pretty close, but not perfect. Here we are with exercise 4 of chapter 13. Now, this exercise does not actually involve any coding. It's just changing a little bit of the code from the previous exercise, and also like doing some thinking and investigations to appreciate what a 95% confidence interval really means given different sample sizes. Now, this also relates to exercise 1. So you might want to have a look back at the figure that you created for exercise 1. That was the relationship between the confidence interval bounds, or the width of the confidence interval, and the sample size. Okay, so here's what you want to do here. Rerun the code for exercise 3, but use a sample size of 50 instead of 500. Okay, and then basically just keep making the sample size smaller and smaller, and just explore how often is the true population mean still contained within the confidence interval bounds, given that the sample size is getting smaller and smaller and smaller. So just as a quick reminder, in the previous exercise, we ran this code multiple times, and we found that approximately 95% of the time, random samples had confidence intervals, 95% confidence intervals, that included the population mean. And we ran it multiple times, and yeah, we always got somewhere around 95%. So that was with a sample size of 500. What's going to happen when we have a sample size of 50? Now, 50 is still a reasonable sample size for many experiments, and but it's certainly a lot smaller than 500. Okay, so now we still get around 95%, somewhere around, let's see what this is here, 95%, slightly above, slightly below 95%. Okay, so, and now let's make this, how about 10? A sample size of 10. That is a pretty small sample, and yet we still get around 95%. Let's see what, yep, extremely close to 95% of samples using a sample size of 10, where the true population mean was contained within the confidence interval bounds. That may seem magical, amazing. How do confidence intervals do that? How does the confidence interval know that the population mean is so close? Especially, going back here, we saw. Let me see. I'm going to uncomment this. So this is the code from exercise 2. So here we see. Oops, no, I want to comment this out. What I wanted to show you is that here we see that the confidence interval is so narrow, it's so tight relative to the sample distribution. So how is it that we can draw such tiny, tiny samples of 10, n equals 10, and the confidence interval is still so tight, and yet it works so well that the population mean is within the confidence interval? Okay, so that is the question. And the answer is that this tightness, the fact that this confidence interval is so small, is because the sample mean in this exercise, the sample size in this exercise, in exercise 2, was quite large. Here, the sample size is quite small. So let's see what is the actual confidence interval. Right here, I'm not reporting the actual confidence interval. I'm just saying whether the population mean is within or without the bounds of the confidence interval. So now here, this comes from, this is just this variable here. So this is just whatever was the last run of this experiment, the last iteration of this experiment using a sample size of 10. So here we see that the actual confidence interval is minus 1.7 to 3.6. So that means, going back here, that this would be, the confidence interval is like here. It's this wide, right? So as the sample size gets smaller, the confidence interval gets larger. So the confidence interval is getting so huge that, that it's no surprise that the population mean is within the bounds of the sample confidence interval. And you can take this even further. You can make this more extreme. How confident can we be that the population mean is between minus a trillion and plus a trillion? We can be really confident that the true population mean is between minus a trillion and plus a trillion. We can be 100% confident that the true population mean is between minus infinity and plus infinity. So this is one of the themes that I want to illustrate with this exercise. And this insight here is, why do we pick a 95% confidence interval? Why don't we just use a 99.9999% confidence interval? Then we can be really, really confident. And so the answer to that question is that the higher the confidence interval, so the closer the confidence interval is to 100%, or 1 if you're thinking about it as a proportion, then the wider the bound is going to be. So you want to be more confident about the true population parameter, you have to make the interval be much, much, much larger. And so that is not necessarily good. So when you're picking a confidence interval, 95% is, trying to find this balance between it being really statistically representative and allows you to make statistical inference, while also avoiding just making the confidence intervals be so wide that they are basically uninformative. Now for exercise 5. This again follows up from the previous several exercises. So make sure you have done exercise 2 and also 3 and 4 before working on this exercise, exercise 5. Okay, so you also don't need to write any new code for this exercise. Basically, in the previous couple of exercises, we used a normally distributed population. So the population data were normally distributed, and we were drawing samples from a normal distribution. So what you want to do now is basically just recreate the data, the population. So you want a population of x squared instead of a normal distribution. So let me just go back up here to exercise 2. So remember, the exercise 2, we generated a population by drawing from normally distributed random numbers. So now for exercise 5, you want to go back to exercise 2 and just square all of these values so that the population distribution is non-normal. So then repeat exercise 2, repeat exercise 3, and I guess you can also repeat exercise 4. So we don't need to do really any significant changes here. We just change this 1 to a 2. So now we are squaring the population data. And remember, this is what the data looked like before. It went from minus 10 to plus 10, approximately. This looks like a normal distribution. This is obviously a normal distribution. Looks great. Let's see what our new population looks like. So it's going to have a power law-like distribution. So the values close to 0 will be very common, and values further away from 0 will be less common. So very, very sharp distribution, lots of data that are very close to 0, and then a very strong decline down here. So we have much more data with very small values and relatively few data points with large values. You also see that asymmetric clustering over here. Okay, so now let's go back to this is still exercise 2. Here we are drawing one sample of sample size of 500, and we just want to see whether we get the population mean inside the confidence interval bounds for this sample. So here you see in light gray the histogram of the sample data. So it's not the population data, it's a random sample of 500 data points. But you see that the true population mean is contained within the bounds of the sample mean. So we still get, this is just one run, but you can run this again. We still get the same principle that we expect for confidence interval, even though the the population is strongly non-normally distributed. So we can run this again multiple times, as I showed in the video for exercise 2. If you keep running this lots and lots of times, here's an edge case. It's almost outside the boundary. Keep running this lots and lots of times. Eventually, you'll find that the sample mean is beyond the is far away from the population mean. You can keep running it. I'm not going to keep doing that here. Okay, so far so good. Now let's go to exercise 3, where we are going to basically quantify what I'm just doing qualitatively here. So we're going to draw 5,000 samples, each of size 500. Remember, before running this, to change this back to 500 if you set this to some much smaller number from exercise 4. Okay, so each sample is of size 500, and we're going to generate 5,000 of these samples. And then we just want to know how often is the sample mean or the population mean contained within the confidence interval bounds of the sample mean, given the sample size and the sample standard deviation. And now this is kind of boring because it's exactly the same as what we saw before with the normal distribution. So the conclusion here is that the confidence interval is still working as expected, even though the population distribution is non-normal. This is due to the central limit theorem that as we sample means, the distribution of sample means is normal, so we can still use this analytic formula for the confidence intervals, and it still works as expected, regardless of the distribution characteristics of the population. Okay, so then what I want to do is make this smaller. So let's go down to a sample size of 50. Now remember, when the population was normally distributed, it didn't matter how small the sample size, we still got that 95% of the 5,000 experiments had confidence intervals that included the true population mean. And it didn't matter when the population was normally distributed. It didn't matter if its sample size was very small or very large. Of course, the actual confidence intervals are different, right? They got really, really large for small sample sizes. So the question is, what happens here? Now we see 92%. That is smaller than 95%, but that's the smallest we've ever seen, right? So now let's try this again with 10. Let's see how this looks. And here we see that when the sample size is 10, we only get 85% of samples have a 95% confidence interval that includes the population mean. So this is a real discrepancy here. It should be 95% because, we haven't changed the confidence interval, right? It's still 95% confidence interval. And yet, this is no longer working as expected. Here we are just seeing 85%, even though we expect to see 95%. So what is going on here? Where does this come from? And why does this happen? So the answer is that confidence intervals based on the analytic formula rely on the central limit theorem. And the central limit theorem only starts to kick in when the sample size is sufficiently large. Now, what does sufficiently large mean? It's always a very difficult but important concept in statistics because lots of things need to be sufficiently large. You'll see this again in I think it might be chapter 16 about statistical power and computing sample sizes. What does sufficiently large mean? But anyway, so somewhere around 20, 30, 40, the central limit theorem starts to kick in. And when you have smaller sample sizes, the central limit theorem is not really kicking in yet. So that's why we get this discrepancy, because we cannot rely on the central limit theorem. So this result is not really trustworthy. On the other hand, why did it work for the normal distribution? There we also had really, really small sample sizes, even smaller than 10, and it still worked really well. Well, there the answer is that the population was already normally distributed. So although the central limit theorem didn't really kick in, the population was so well behaved, it was already so nicely Gaussian, that these samples are likely to be Gaussian just because the population is so Gaussian. So basically, what you want is to, in practice, you want to have either really large samples so that you can rely on the central limit theorem, or you have a perfectly normal distribution, population distribution, so that your small samples are more likely to be normally distributed, and therefore you won't need the central limit theorem so much. The last thing I would like to do out of curiosity here is to see what is the actual confidence interval. So this is pretty wild because the confidence interval goes from -1 to +25. So first of all, that is a huge range, right? If we go up to this plot here, -1 to +25. So that is a really, really large confidence interval. So it's not that surprising that the population mean is going to be not 90% of the time, 95, but at least, over 80% of the time within that bound. But the confidence interval is also a little bit weird because it's negative. The lower bound of the confidence interval here is negative. It's a minus number, and that doesn't make any sense given our population because this population is defined as x squared. So it is literally impossible for any single data value to be negative. No, these are strictly non-negative values. In fact, you're not even going to have any values of 0 because just the chance of getting an exact value of 0 from drawing, floating point random numbers is basically nil. So we have strictly positive value data, and yet the confidence interval can be negative. So that is mathematically possible when using the analytic formula, but it doesn't make any sense. It's not interpretable. This is another sign that that we should not be using confidence intervals in this particular case. And the problem here is the really small sample size. So, if we would go back to 500, and then we see what this confidence interval actually is. Okay, so here you see it's 14 to 18. So this looks much better. So now the central limit theorem kicked in because we have a large sample size. But going back, this small sample size with an impossible data value here for the confidence interval, this is a limitation of using the analytic formula for computing confidence intervals, and that is one of the motivations for empirical confidence intervals via bootstrapping, and that's what we are going to explore in the next several exercises. Welcome to exercise 6 of chapter 13. In this exercise and the next maybe 4 or so exercises, we are going to focus on empirical confidence intervals obtained via bootstrapping. So this is a computational empirical method to get confidence intervals. It's really useful for two kinds of situations. One is if your data do not conform to parametric statistics assumptions, and you saw what can happen to confidence intervals in simulations in a previous exercise when the data are non-normally distributed. So that's one advantage of bootstrapping for empirical confidence intervals. Another situation is that the confidence intervals via the analytic formula that we've been working with so far is only defined for the sample mean. Now, that's great because there are many, many situations where you want confidence intervals around the mean. But there's also many other situations in statistics, in machine learning, in signal processing, in lots of applications where you want to get confidence intervals around some other kind of statistic. Maybe it's a correlation coefficient. Maybe it's a spectral analysis. Maybe it's a cluster size in some kind of geographical mapping research. Anyway, so computational statistics are great. And what you are going to do in this exercise is basically implement code to perform bootstrapping to get confidence intervals. It's actually quite straightforward to do it. Obviously, I will show you the code in a moment with explanation. Your goal is, there's two parts to this exercise. First, to produce a figure that looks like this. You will recognize this kind of figure from a couple of exercises ago. We created a figure that looked like this. It might have been exercise 2. There we used the formula, the analytic formula for confidence intervals. And here we are just using bootstrap confidence intervals. So we have here the sample histogram in light gray. And then we have the sample mean in here and the true population mean, which we know because we simulated these data. You can see visually in this particular case, the population mean and the sample mean were very close to each other. And then what you see here, this dark histogram here, this is the distribution of bootstrapped means. So these are the sample means that are obtained from repeatedly drawing from the sample, not from the population, but from the data sample with replacement and computing the average of that bootstrap sample. So we repeat this lots of times, hundreds of times, or a couple thousand times. Number is up to you, and I discuss in the book, of course, how many iterations to use. And then you get the 95% confidence interval in this gray bar here. And I mentioned in the text here that there's a lot going on around x equals 0. So once you produce this figure, you might want to zoom in so you can better grasp all of the different features of these data that are being plotted here. Okay, so writing code to produce this figure is the first part of this exercise. The second part of the exercise is to compare the analytic confidence interval and the empirical confidence interval. So this confidence interval is the same as what you get from creating this figure up here. And then you compute the analytic confidence interval using the formula. And you're not going to find a perfect match, obviously, because this is an empirical shuffling-based, randomization-based method. But because these data are normally distributed, because the sample size is large enough, the central limit theorem kicks in, and you should find that the empirical confidence interval and the analytic confidence interval are pretty close to each other. They should be quite a good match. Okay, so now I will switch to Python and I'll walk through all of my code. Here we are in exercise 6 code. So you can see I have a sample size of 500. I'm going to use 1,000 iterations or shuffles or repeated resampling in the bootstrap procedure. And now here is where I'm drawing a sample from the population. Now, this variable is not defined anywhere here. This is a variable that was defined earlier in exercise 2. So if you're just popping into this in a fresh Python session, then you're going to get an error here. And so you need to go back up to the code for exercise 2 to rerun that code to recreate this population here. Okay, so then, we get the sample mean and the sample standard deviation. Here is the method for bootstrapping. You can see it's very simple. So we loop over all of the shuffles, the number of iterations. And then here I'm randomly choosing from the data sample the same as the sample size. So we have our data sample, which is 500 data points randomly sampled from our population. And then I choose with replacement, because replace equals true is the default for random.choice, the same sample size as this. So there's 500 numbers here. There's going to be 500 numbers here. Because this is bootstrapping with replacement or sampling with replacement, some of these numbers are going to be repeated and some of these numbers, some data points in here, are going to be omitted. It's just happening by chance. Okay, so then we get our bootstrap sample and we compute the mean. It is that simple. And then we repeat this lots and lots of times. Here I do 1,000 times. So I like writing this code out in a for loop here because I think it makes it very clear for you what is the mechanism underlying bootstrapping. Super simple, super straightforward. If you're really into writing compact Python code and you really like list comprehension, you can also use this line. This does exactly the same thing as these 3 lines, just in one line of text. Okay, so then we get our confidence intervals. This is B here for bootstraps. We have our bootstrapped empirical confidence intervals, and that is just the values corresponding to the middle 95% of this distribution. So 2.5% on the bottom, 97.5% on the top. So this gives us a two-tailed 95% confidence interval. Okay, so we can run that code. And then we can just generate the plot here. So you can see, that's another thing I need to run from earlier in the exercises. Okay, so yeah, there was just another variable in here that I defined earlier and I didn't rerun here. Okay, so here we see the plot. Now let me uncomment this line just to zoom in to this plot. So you can see right now we go from -13 to +13. I'm going to rerun this code, and that's going to give us basically -1 to +1. So here in the light gray is the data histogram. This is the histogram of our sample that we drew from the population. Now this is obviously not the entire distribution. Here, you see much tighter distribution is the bootstrapped mean. So this is the histogram of this variable here. It's the means, 1,000 means of all of these random shuffles of or random resamples of these data. And then we have the 95% area of this distribution, and that is our 95% confidence interval area. Okay, and then we see, in this case, the population mean and the sample mean were very close to each other. Okay, so that was all the first part of this exercise. The second part was just to compare this against the analytic formula for the confidence interval. And as I showed in the book, you're going to find that these are quite close to each other. Here we are with exercise 7 of chapter 13. What we are going to do in this exercise is expand the implementation of bootstrapping to obtain confidence intervals from a sample mean to a sample correlation. So this is a really great example of how you can use bootstrapping and computational statistics to get confidence intervals for statistical characteristics other than the sample mean. Okay, so here's what you want to do. Simulate a pair of correlated data vectors with 100 data points, or it's actually 200 data points in total because you need two variables. And the correlation between the two is 0.3. So you have a population correlation of 0.3, and then you simulate a pair of 100 pairs of numbers and impose that correlation on them using methods that you learned about in the chapter on correlation coefficient. Then you want to compute an empirical confidence interval of that correlation coefficient, the sample correlation coefficient, based on the sample that you have here. Now, be mindful, the concept is the same as in the previous exercise, but the implementation is going to be different. So it's the same idea, the same principle, but the code is going to look slightly different. So just be mindful of what exactly you are shuffling and how you are shuffling the data here. Okay, so then basically what you want to do is put that code into a function, a Python function, where you can input the sample data and return the confidence intervals and all of the bootstrap coefficients. Now you want this in a Python function because this function we are going to use in the next several exercises. So this exercise is setting up code that you will need for the next several exercises to continue exploring empirical confidence intervals in correlation coefficients. Okay, so yeah, then basically the null hypothesis of a correlation coefficient is 0, is r equals 0. So we can say that if the correlation is statistically significant, then at the alpha equals 0.05 threshold, then 0, so correlation coefficient of 0, should be excluded from the confidence interval bounds. Let me explain that again. So you have your empirical correlation between a pair of variables. You compute a confidence interval, a 95% confidence interval around that correlation coefficient, that sample correlation. If you find that 0 is included inside the confidence interval bounds, the correlation is not statistically significant. On the other hand, if you find that the correlation is outside the confidence interval bounds, then the correlation coefficient is statistically significant at a 0.05 threshold. Okay, so then you can make a plot that looks like this. So here you see the true population correlation and the sample correlation that you see are pretty close. The true population correlation is 0.3. As specified, as you know by now, the sample correlation should be pretty close to 0.3, but not exactly because of random numbers, just random chance. Here, this gray histogram is the bootstrap distribution of, the histogram of the bootstrapped correlation coefficients. So sometimes you get much stronger correlations, and sometimes you get correlations of 0 or maybe even negative, a slightly negative correlation coefficient. Okay, and then here are the confidence intervals. So then you see 0 is excluded from the 95% confidence interval, and this we interpret as indicating that the sample correlation coefficient is statistically significantly different from 0. And up here in this title, I'm showing that this is the Pearson correlation coefficient. You can compute the p-value here from the scipy.stats.pearsonr function to get the true correlation, Pearson correlation, and the true p-value. Here I'm listing the parameters, and here this code is a little bit different. The concept is the same, the math is the same that we have used in previous chapters to simulate correlations. The only difference here is that I'm defining this to be a matrix instead of two variables, right? So normally I create two variables, x and y, or x1 and x2. Here I'm putting them in a matrix, and the reason why I'm putting them in a matrix is because I want to get all of the correlations using NumPy. So I get the correlation matrix with NumPy. So here we see the empirical correlation was 2.55, which is pretty close to the true population correlation of 0.3. Okay, so here I'm defining a Python function. It inputs a matrix, or it takes as input a matrix where the columns are the variables and the rows are the observations. And this optional input here, the number of iterations or shuffles in the bootstrapping, which I'm defining to be 1,000 if no one provides any input there. Okay, and then I call this function core CI. Obviously, this stands for confidence interval. Okay, so here is the idea of bootstrapping for correlation coefficients. So what you want to do is randomly choose rows with replacement from this data set. And then you compute the correlation coefficient of the data, but only for those rows. And some of these rows will be repeated, some of these rows will be omitted. This is what happens when you're doing random sampling with replacement, which is what NumPy calls random.choice. Now notice, if you are already familiar with permutation testing, notice that we are not changing the mapping between the two variables. So it's not like we are shuffling the mapping between column 1 and column 2. If you are inclined to do that, then that's great, because it means you're already prepared to learn about permutation testing, which is the topic of a later chapter. But that is not what we are doing here. You want to preserve the pairs. You don't want to shuffle the pairs. You want to keep the pairs together. It's just that you randomly sample from some rows and not other rows. So then the rest of this code is really, really similar conceptually to the code from the previous exercise where we were bootstrapping for sample means. And then here I return the 95% confidence interval from this vector of bootstrap correlation coefficients, and I'm returning that entire vector itself. This is, we're going to use this basically to plot histograms and so on. Okay, so, so that's the end of the function. And then we compute the Pearson correlation coefficient between these two variables. This also gives us the p-value. So here I call the function on these data, and then here is the plotting. So we can see that we get a nice result. So the observed correlation is, the sample correlation is a little bit smaller than the theoretical population correlation. You can also see there was some correlation, some bootstrap correlations, just random. I mean, this is just by chance. It's all exactly the same data. We're not shuffling. We're not generating new data. This is from exactly the same data, but sometimes we just happen to pick rows and exclude other rows and repeat some rows such that the correlation ends up being very close to 0. So we can run this a couple of times. You can see so far, all these times I'm running the correlation, the correlation coefficient would be considered statistically significant because, oh wait, okay, so I just ran this code a couple of times, just randomly to get a smaller correlation coefficient. What I wanted to show you is that I've added a little bit of extra code in here to say that if the confidence intervals include 0, then make this be red. So this shading here is gray if the confidence interval excludes 0, meaning the effect can be considered statistically significant. If this 95% confidence interval includes 0, then make this patch red. So that you see here, fill between, and then the color is this variable area color, which I set to red. And what is this condition here? So here I say if the sign of the lower bound of the confidence interval equals the sign of the upper bound of the confidence interval. Now, if you have confidence intervals that are on the same side of 0, then this is going to be true. But if the lower confidence interval bound is negative below 0 and the upper confidence interval bound is positive, so above 0, then this expression here will be false, meaning that the color changes to red. Okay, so let's try running this. And beautiful. Now we see this finding would not be considered statistically significant. It's very, very close. I mean, you can see also the p-value is very close to the standard threshold of 0.05. And yeah, basically this just overlaps a tiny bit with 0. So we can rerun this multiple times. Yeah, brilliant. You might see situations like this. I'm actually going to talk more about this in a later exercise, but this is a pretty interesting case where the Pearson correlation coefficient had a p-value that was above the significance threshold, but the confidence interval just a tiny, tiny bit excluded 0. So, I mean, you'd have to zoom in to really see what's going on here. Actually, we can see what is this variable called? This variable is called CI, I think. So I'm just curious what the actual lower bound is here. Okay, so the lower bound is a correlation coefficient of 0.0028. So that is technically above 0, but it is really, really, really close to 0. Anyway, I hope that you enjoyed this exercise and learning how to extend the concept of confidence intervals to other statistics, including correlation coefficients. Welcome to exercise 8 of chapter 13. This exercise and the next exercise go closely hand in hand together. So I recommend setting aside a block of time to do these two exercises in conjunction. Okay, so the goal of exercise 8 is to explore the impact of sample size on the confidence intervals around a correlation coefficient. So you're going to use the function that you created in the previous exercise to determine what is the impact of increasing the sample size on the width of a confidence interval around a correlation. So a lot of the code for this exercise you can copy from the previous exercise. So in particular, you want to create pairs of random numbers that have that are drawn from a population with a true population correlation of 0.3. Of course, the sample correlation coefficient should be somewhere close to 0.3, but not exactly 0.3. Okay, so then what you want to do in a for loop, this is the key variable to manipulate in the experiment here, vary the sample size from 10 to 3,000 in steps of 100. So basically, the first iteration of this for loop, you generate a pair of random variables with sample size 10, impose a correlation of 0.3 on them, and then compute the bootstrap confidence intervals around that correlation coefficient. So that's the first iteration in the experiment. In the next iteration, you do exactly the same thing, except now the sample size is 110. And then the next iteration is 210, and so on. Okay, here I have a little note over here to the side that says, this experiment takes a while to run, so once you set it up, you can press run and then go check your email or watch some TikTok videos. Or you can reduce the number of bootstraps from 1,000 to 500. That's just to reduce the computation time. Okay, so then basically you want to produce a figure that looks like this. So here we have two panels. This shows the sample size on the x-axis, the sample correlation coefficient on the y-axis. This dashed gray line here is the true population correlation, and the error bars around each dot, which is the sample correlation, correspond to the 95% confidence interval. And what you see, well, actually, I'm going to interpret this more in the code when I show you the code. Okay, and here in panel B, we have a confidence interval range. This is literally just the distance here. So the distance from this value to this value, you can see that's very large. Here, when we increase the sample size, the distance between the two confidence interval bounds gets smaller, and so on. Again, I'm going to have a few remarks about this plot when I switch to Python. So here is the range of sample sizes. And let's see, here's the main experiment here. So we're looping over all of these sample sizes. I generate n. So the n is now the variable corresponding to each element in this sample size array, which is up here, for each iteration. So generate sample data with the same correlation that I specified in a previous exercise. So correlation of 0.3. Here I take the observed correlation coefficient, and here I get the confidence interval bounds from this function core CI, which we created in the previous exercise. And here you can see I'm only taking the first output of this tuple, the output, the first element of the output of this function, because in this exercise, we don't actually need all of the bootstrapped correlation values themselves. We only care about the actual confidence intervals. So that goes into this matrix here. And then, then I do a bunch of plotting. So I'm making error bars for the sample sizes on the x-axis, the observed correlation, so the sample correlation, and then I have the mean correlation, so the correlation minus the bootstrap interval, and then the observed correlation plus the upper bound. Okay, and then, here is the horizontal line for the population correlation. And then here is the difference between the lower bound and the upper bound for all of the bootstrap results for all the different sample sizes. Okay, so then we get this figure that reproduces the figure that I showed in the book. Oh yeah, it takes a few seconds to run this. Okay, not so bad. It took 8 seconds, so that's actually only one really, really fast TikTok video. Okay, so what's interesting about this plot is that you see that the correlations are converging to the true population correlation with increasing sample size that is expected based on the law of large numbers applied to a correlation coefficient. And you also see that the confidence intervals are getting smaller as we increase the sample size. That you also see here for sample size of 10. I mean, that's especially for a correlation coefficient, sample size of 10 is really, really small. So the confidence interval bound is very large, but it quickly drops down. But then, it's pretty interesting to see here and also here that the benefit of increasing the sample size decreases with increasing sample size. So basically, there's a huge difference between a sample size of 10 and 1,000 in terms of the accuracy, the confidence interval, but there isn't really much of an advantage between a sample size of 1,000 and 3,000. There is, you can see the confidence intervals are getting smaller, but that difference between, 10 and 1,000 is big, but the difference between 1,000 and 3,000 is small. So one of the take-home messages here is that increasing your sample size is only helpful up to a certain point. This is an issue that I will come back to in the chapter about power and sample size, and also the chapter about biases and avoiding potential biases and doing proper statistics in practice. Now, the thing is, when you're simulating data, it doesn't matter. Just generate sample sizes of 1 quadrillion. Who cares? It's just computation time. But in the real world, there are practical limitations on your time, on budget, research, financing budgets, and so on. And so, you have to make real world decisions about how big your sample size should be. So I hope that simulations like this will help you understand that arbitrarily collecting more and more data is not necessarily going to give you better results once you have a sufficient sample size. Welcome to exercise 9 in chapter 13. This exercise follows directly from the previous exercise, including using a lot of the same code. So if you haven't done the previous exercise, make sure you do that one before trying to work on this one. Okay, so in the previous exercise, exercise 8, we manipulated the sample size while keeping the population correlation fixed. And what we are going to do in this exercise is basically the complement. So we're going to keep the sample size fixed at 50 and vary the population correlation from 0 to 0.99 in 42 steps, because 42 is a great number. Okay, but otherwise the plotting is really similar. So here you can see I'm plotting on the x-axis the population correlation. And of course, the sample correlations are going to be different from the population correlation, although, they should be relatively close. Interesting to see that in most cases, the population correlation is included inside the bounds of the 95% confidence intervals. But there are cases where the sample correlation was higher than the population correlation. And there's probably also going to be some cases where it happened to be lower that you can see here. Okay. And so, so I'm going to have more to say about this in the code. And this is also basically the same plot as in the previous exercise. This is the confidence interval range. So the distance between this point and this point for each of these different iterations in the experiment simulation. After completing the previous exercise, I hope you find that this exercise was relatively straightforward. In fact, you could have just copied and pasted the code from the previous exercise here and just modified things as necessary. So you can see this is one change. I'm varying the correlation coefficients, the population correlation between 0 and 0.9. Here I fix the sample size. It's always going to be 50 for all of the iterations in this experiment. Otherwise, some variables are changing here and there. Here is R instead of true R. So this is variable R, which comes from here, which is corresponding to each element in this vector coef. Okay, and then, I'm using this same core CI function that we wrote a couple of exercises ago. All right, and then, the plotting is also basically the same except for the legends and so on. So what do we see here? So we see that the confidence interval widths are getting smaller as the magnitude of the effect, so the effect size is getting larger. So that's interesting because here the sample size is exactly the same. In the previous exercise, we saw that as the sample size increased, the confidence interval bounds decreased. And here we are seeing the same phenomenon of shrinking confidence interval bounds, but this is not due to the sample size, this is due to the effect size. So the stronger the effect, the less data you need to have a high precision confidence around your sample estimate. So that's one interesting thing you see here. You can also see that these confidence interval bounds are asymmetric. So in this one, for example, let me see if I can open this up a little bit more. So you can see here, for example, that the upper bound is closer to the sample correlation coefficient compared to the lower bound. So these confidence interval bounds are asymmetric. That's an interesting and unique property of empirical confidence intervals that you get through bootstrapping. This is not a kind of thing you can get with the analytic formula. When you use the analytic formula to compute bootstrap confidence intervals around the sample mean, the confidence intervals are symmetric. Okay, and then, this is just another visualization of what we see here, that the confidence interval boundary is getting smaller for these larger effect sizes. Here we are with exercise 10 in chapter 13. The goal of this exercise is to explore using confidence intervals for doing statistical inference, basically to be able to label a finding as being statistically significant or non-significant. So this and the next exercise will deal with the relationship between uh, statistical evaluations based on confidence intervals versus t-tests. For parametric statistics, that's in this exercise. In the next exercise, we will explore confidence intervals for statistical inference in non-normal distributions. Okay, so what you want to do here in exercise 10 is implement these two formulas. So here we have the analytic formula for confidence interval. Here is the obviously the t statistic here. This is just referring back to a previous chapter, which I haven't compiled here. Anyway, so these two formulas implement in Python. And then what you want to do is use these formulas to determine the statistical significance. So just a binary decision, significant or non-significant, for a range of means, so sample means, from 0 to 2.5, and a range of standard deviations from 0.5 to 5. Okay, and then, yeah, you're always testing against the null hypothesis of 0. So now you don't actually need any data for this, right? You need a t-statistic, which you create by having a sample mean and a sample standard deviation and a sample size. And I think I set the sample size to 30. Let me see where that is. Okay, so I haven't specified a particular sample size, so you can actually specify whatever sample size you want. So you don't need data. You just need these statistic characteristics, the mean and the standard deviation and the sample size. And then you can compute the analytic confidence interval and determine whether 0 is included in that 95% confidence interval. And then you can compute the t-value, and then you can get a corresponding p-value and determine whether the p-value is less than 0.05. Okay, so then what you want to do is build up a matrix that looks like this. So here we have the sample means and the sample standard deviations. And you see there's only 3 possible colors in this matrix, in this image. It's either 0, 1, or 2. Now, the matrix, the element in the matrix should be 0 when both tests give a non-significant result. So here you can see the standard deviation is large and the mean is relatively small. So these samples will be non-significantly different from 0. So the t-test and the confidence interval both indicate non-statistical significance. And then here, these white areas here indicate pairs of sample characteristics where both the confidence interval and the t-test gave the same results about statistical significance. So the t-test was significant p less than 0.05, and the 95% confidence interval excluded 0. Okay, and then where there's going to be ones, gray pixels, that's where you have one test giving you one result and another test giving another result. So for example, let's say the t-value had a p-value less than 0.05. So the t-statistic is significant, but the confidence interval included 0, indicating non-significance. So if you get a conflict, a divergence between the t-statistic and the confidence interval, that's when you would label that as a 1. Now you can see there's no gray pixels here. It's only black or white. So that means that there was never a single situation here in this simulation. There was never a pair of parameters where the two different statistical methods for determining significance gave a different result. There was never conflict. They always led to the same conclusion. Okay, so that is the point of this exercise. So here we are in Python. You can see I'm specifying the means and the standard deviations, and I use a sample size of 30. So here is the double for loop over all of the means and standard deviations. Here I'm computing the standard error of the mean. Here I get the confidence interval using the analytic formula. Here I compute the t-value. Now, this is just, the numerator is just the mean value because we are testing against the null hypothesis of 0. So implicitly there's, a minus 0 in here. Okay, and here I get the p-value, the two-tailed p-value based on this t-value and the degrees of freedom. And here's where I build up the matrix. So I say that this element in this statistics matrix is, it's going to be 0 or 1. So I add, it starts off as being all zeros. Let me show it here. So I initialize this matrix to be zeros, and then I'm going to add onto it uh, this. So let me see. So this is a Boolean. This is the lower bound of the confidence interval. And we want to know whether the lower bound of the confidence interval is negative, whether it's below 0, which would mean non-significant, or whether it's positive, which would mean significant. So this is a Boolean. This returns false or true, depending on whether this is negative or positive. And then I convert that Boolean into an integer. So basically, this becomes 0 if it's non-significant, if the confidence interval includes 0, or it becomes 1 if the confidence interval excludes 0. Okay, and then same story here. So the p-value from the t-value, and then if it is statistically significant, then that's going to be true here, which gets converted into a 1, and then I add that onto that element of this stats matrix. Okay, and then I just show this matrix. So here we see the results, and this is not so interesting to look at because it's the same thing I showed in the book. Here, this is just a little bit of extra code just to see what are all of the unique numerical values in this matrix. All the elements in this matrix are either 0 or 2. There is no case where we got a 1 in this matrix. So that's pretty interesting. That shows that at least for data that conform to assumptions of parametric statistics, in this simulation, we see that there was no situation where the confidence interval and the t-test gave different conclusions about the results. Now, if you like, what you can also do is explore other ranges of p-values. So here, hard coding this to be 0.05, and here this is also 0.05 corresponding to a 95% confidence interval. So you can try setting this to be, a 99% confidence interval. Now, if you change the p-values for the two analyses, it's not surprising that you will see differences between them. But that's not surprising because the two analyses have different statistical thresholds. So if you really want to compare them, you need to make sure you set the p-value to be concordant. So a p-value of 0.01 corresponds to a confidence interval threshold of 0.99. And then we will also see here again that there's no gray pixels. The diagonal has shifted because we changed the p-value. But the important take-home message from this exercise is that the confidence interval and the t-test lead to the same conclusions about the data. We are going to explore that using non-parametric, bootstrap-based confidence intervals in the next exercise. Now for exercise 11. This exercise is a conceptual follow-up to the previous exercise, although it's going to be slightly different. So what we're going to do here is use bootstrapping to determine statistical significance in an independent t-test where the data violate the assumption of normality in the t-test. So here's what you want to do. Create two samples. So you want two variables, two little data sets, each variable of 30 data points. So sample, I call this S1. So sample 1 is standard normal distributed random numbers. And then sample S2 is kind of the same. It starts out the same way. So 30 numbers randomly drawn from a standard normal distribution, but then you square all of those numbers. So that's going to give you a normal distribution and data with a non-normal distribution. Okay, and then what you want to do is force the mean. So change the mean of sample 2 so that the mean is exactly 0.5. Okay, so then let's see, your goal is to bootstrap to generate a confidence interval, a 95% confidence interval around the difference between the sample means. Okay, so here I just say I haven't yet explained in the chapter how exactly to do this, but I think you'll figure it out. If you are struggling to figure it out, then, well, I'm going to explain it in a moment. Okay, so then you want to produce a figure that looks like this. Here on the left, we see the histograms of the two data sets. Now, there's not that many bars in this histogram, but these data sets are quite small. They're only 30
data points each. So you see sample 1 is clearly normally distributed, and sample 2 in the light gray boxes is clearly non-normally distributed. Now, the distributions themselves are different, but when we do bootstrapping of the difference of the means, then you get a normal distribution. That's not so surprising because of the central limit theorem and so on. So this histogram here is the distribution of the bootstrap mean differences between these two samples. So, and then you see here is the center, and here is the 95% confidence interval. Now, what you see here is that the confidence interval excludes 0. So 0 is our null hypothesis value. So based on the confidence interval from bootstrapping, we would say that these two distributions have a statistically significantly different mean based on the empirical bootstrap 95% confidence interval. Okay, and then here I'm performing an independent sample t-test. You can see that this is also statistically significant. Now, we can debate whether it's appropriate to use a t-test given the distribution shape of sample S2, but what you do see is that in this particular case, the t-test and the confidence interval gave us the same statistical conclusion. In other words, both of these tests, the t-test and an empirical bootstrapping confidence intervals, told us that the two samples have a statistically significantly different mean. So then what I would like you to do is rerun this code a bunch of times to regenerate new data, run the bootstrapping over again. And basically, if you run it lots of times, you will probably find cases where, well, let me start in the positive way. You will find that in most cases, the results will be concordant in the sense that when the t-test is significant, the confidence interval is significant. When the t-test is non-significant, the confidence interval is non-significant. You might find some runs where randomly you get a divergence that's different from the previous exercise where we found perfect concordancy between the t-test and the confidence interval. Okay, so let me switch to code and I'll show you the Python solution. So here I generate sample 1, standard normal distributed data, and here you can see the same code for sample 2, but then I square it. And here I take the sample to minus its empirical mean plus 0.5. So this mean centers and then shifts. Basically, this guarantees that we will have a sample mean of 0.5. Okay, and then I compute the t-test. In this case, I don't print, well, I'll print it out in the next, in the figure down here. Okay, so let's see. So I'm going to do 1,000 bootstraps. Here is the observed difference of sample means. We're going to need this later. Here I'm initializing a variable called bootstrap diffs. And so here is how bootstrapping works for the independent samples t-test. So we bootstrap randomly from sample 1, bootstrap randomly from sample 2. This is just standard, plain, normal, run-of-the-mill, vanilla bootstrapping, exactly how you used it before. It's just being done independently for each of these two samples. And so that gives us two means, the mean, the bootstrap mean from reshuffling sample 1 and the bootstrap mean from resampling with replacement from sample 2. Of course, the sample sizes are always the same here. And then you just subtract the two means. So it's very straightforward to implement bootstrapping for confidence intervals for the difference of means between two samples. Okay, so then here I get the confidence interval bounds from bootstrapping. Same code that you've seen before. This code you've also seen before. I'm just evaluating whether the sign of the lower bound and the upper bound is the same. Now, because the null hypothesis value is 0, this is an appropriate way to determine whether the confidence interval includes 0 or excludes 0. This code is not general. If the null hypothesis value were 10, if we were evaluating against a null hypothesis of 10, you would need to write some extra code here. So this is really, this code works because the null hypothesis value is 0. Okay, so then just some visualization code with the histogram and so on. Okay, so let's see what these two results look like. Okay, so here we see that the confidence interval includes 0. So in this case, the empirical bootstrapping analysis told us that the means of these two samples are not significantly different from each other. So that's why this is plotted in red here. And then we see the t-value is small and the p-value is larger than 0.05. So a different statistical conclusion from the figure that I showed in the book. But the important thing is that the t-test and the confidence interval test were exactly the same. They gave us the same result in the sense of leading to the same conclusion about the data. So now I'm just literally going to run the code again, exactly the same code, just generating new random samples. And here we see again, non-significant t-test and non-significant bootstrap difference. Okay, so I ran it again. Now again, concordancy, so significant t-test and significant confidence interval test. These are all different samples that I'm generating each time I rerun the code. So it's not so surprising, also with relatively small sample size, it's not so surprising that the result will be significant sometimes and non-significant other times. These are small data sets that we are randomly drawing. Okay, so I ran through this code about 10 times and I didn't find a single instance where I got a divergence between the t-test and the confidence interval test in the sense of one test giving me a significant result and the other one giving me a non-significant result. And then I just got bored of trying it over and over again. So it does happen, but it's relatively infrequent. It just happens because we're working with so much random data here. If you're curious, if you would like to do a little bit of extra challenge for yourself, you can put this code here for this exercise into a for loop and test over 1,000 different times. So basically 1,000 times you generate new data, 1,000 times you do the t-test, 1,000 times you do the bootstrapping, and then you count how often it happens that the t-test gives you a significant result while the confidence interval gives you a non-significant result, or vice versa. I would guess it happens occasionally, not never, but not super often. Welcome to exercise 12 of chapter 13. Here we are going to revisit an exercise that we implemented in chapter 8. That was the chapter on probability theory. You might remember we discussed this kind of silly experiment that always comes up in statistics books about drawing marbles randomly from a vase. And there we looked at the difference between probability and proportion. So the probability of drawing a marble at random versus the proportion of total marbles in the jar. Okay, so you might want to go back and reread exercise 8 in chapter 8, or find the video for exercise 8 of chapter 8 and rewatch that. Or maybe you have an amazing memory and you don't need to do that. So basically what you want to do is get that code, copy all of that code, paste it into a new code cell for this chapter, for chapter 13. And all you want to do is add these error bars here. So previously we generated exactly this figure, but it was just the probability and the proportion based on randomly sampling from that jar with replacement. So here what you want to do is add this error bar, which corresponds to the 95% confidence interval around the empirical proportion. So you're only drawing one random sample from the jar with replacement, but then you want to bootstrap within that sample. So you're not bootstrapping by drawing again from the jar, you're only bootstrapping from the sample that you took once from the jar. Okay, and then basically what you should find is that the true probability, the theoretical, the analytic probability should be contained within the 95% confidence interval of the proportion. Obviously, if you run this code lots and lots of times, you're going to find some cases, it's going to be rare, but we expect it to happen on 5% of the time. But there's going to be times when the proportion is outside the confidence interval bounds. Anyway, so this is the goal of this exercise. And now I'll switch to Python and show you my code solution. So you should recognize a lot of this code from chapter 8. So we have, these marbles, the total number of marbles. Here I'm putting them all into a jar virtually. And here I'm drawing a random sample. Now, Notice the difference between these variables. I have variable jar. This is all of the marbles that are in the jar. And then I have the marb sample variable. This is the random selection. This is us reaching into the jar 500 times, pulling out a marble, looking at the color, and then putting the marble back in. So sampling with replacement 500 times from the original jar. You can think of this jar as like the true population, and this is our random sample from that population. Now, the sample is actually bigger, the sample size is bigger than the population because we are sampling with replacement. Okay, so then now here's the new code here, all this bootstrapping stuff. This is new. So over all of these bootstraps, we have another choice. Now, this is what I wanted to highlight. Here, I'm randomly drawing marbles from our sample. I'm not drawing a new sample from the jar. I'm just resampling with replacement 500 times from the sample that we already took from this population, from the jar. Okay, so this is basically our bootstrap sample. And then here I'm computing the empirical proportions of the how often we saw the different colors in this sample. Okay, so then here we get the confidence intervals. Obviously you recognize this code with a percentile. We need this 3 times, right? Because we have 3 different confidence intervals for 3 different colors of marbles. Okay, and then the rest of this code is the same as in chapter 8. This code is new, putting in these error bars, and let's see how it looks. So you see, this is a really tight match over here. That looks good. In all cases, the probability, the true probability, is contained inside the bounds of the empirical confidence interval for proportion. Now, we can, just kind of qualitatively note the size of these error bars here, the width of the confidence interval bounds. And now what I'm going to do is increase the number of draws, the number of times we pull a marble out, from 500 to 5,000. So now what you see with a larger sample size, that the confidence interval bounds got smaller. So this is something that you have observed before. You can see it when you look at the formula, the analytic formula for confidence intervals. It's related to the square root of the sample size. You've also confirmed this empirically before with the correlation coefficient exercise, for example. And now here you see it again for proportion. And it's pretty interesting. Let me zoom in here. It looks like for this case, it looks like the the true proportion probability might be just, I don't know, inside or outside. It's very close. This could be the case where the confidence interval actually technically excludes the true population value. But the main point of this exercise is that now you have seen several different ways of adapting the code for computing empirical bootstrap-based confidence intervals for sample means, for correlation coefficient, for the difference between sample means, like in a 2 independent sample t-test environment, and now also for proportion. So empirical confidence intervals are really versatile. You can use them for many different statistical characteristics. Now for exercise 13 of chapter 13. So we're going to apply confidence intervals to real data. And as I write here, there's no new conceptual points in this exercise. The idea is just to give you some more experience working with confidence intervals in real data before and after cleaning. Okay, so here is the goal. You want to go back to this heart arrhythmia data set that we worked with in chapter 7. So revisit the code for that chapter, copy and paste a bunch of the code for importing those data and processing those data, cleaning those data. In particular, you want to remove the outliers defined as any numerical value greater than Z of 3.09, an absolute value. So any Z-score values less than minus 3.09 or larger than plus 3.09. So identify and remove those data points from the data set, but do not overwrite that data set. You want to have 2 copies of the data set. the original data, uh, right how you import it, and then the copy of the data set that is cleaned according to this z-score threshold. Okay, and then you want to compute and print the 95% confidence intervals around the mean of each column, so each feature in this data set before and after outlier removal. Now, in my solution, I used the analytic formula. You can use the analytic formula for confidence intervals. If you prefer, you can also use bootstrapping to get empirical confidence intervals. It's up to you. It's fine how you want to do it. Be mindful that when you identify these outliers, you replace them with NANs, and you have to be careful of what's going to happen to those NANs when you work with the data, when you compute the means and the standard deviations and so on. So be aware of that. And then you can print out your results here. So you can see for each feature, each column of the data, I have the initial and clean. So this is the raw data, how it's imported. This is the clean data after removing outliers. Here I have the mean plus or minus the confidence interval. So this is a point estimate format of reporting means and confidence intervals. Now you can see that in this case, for the variable age, these two numbers are identical. So that means that there was no outliers. So the data were exactly the same before and after cleaning. Same thing with sex, no outliers. But here you start to see some differences. So here is height. These numbers are different. These numbers are different, and so on. In fact, I think all of the variables, so every variable is different before and after cleaning, except for age and sex. Okay, so I have a few comments that I want to make about this, but I want to show you my code first, and then I will get to the interpretations. All of the code here in this cell should be super duper familiar. I'm not doing anything new, literally just copied from chapter 7. So here I import the data, I make a copy of the data, z-score all the columns in those data, and then here I'm replacing any of the data values that are greater than the threshold, and it's the absolute value of those Z values with NANs. Again, this is all code you've seen before. Okay, so now I'm looping over all of the columns, and here I compute the mean, the standard deviation, and the sample size. Here I get the confidence interval using the analytic formula, report that out, and then this code is exactly the same, but for the cleaned data. So this is the original data, how I imported it from online, and this is the cleaned data after the z-score thresholding. Okay, and then, probably helps to run this code first. Okay, so here we see, so as I showed in the book, I'll zoom in a little bit, these values are unchanged, so there were no outliers removed. These values are unchanged, no outliers to remove. Everything else, it's interesting to see that sometimes the mean goes down when we clean. So here the mean gets smaller after removing outliers. So that means the outliers were on the right tail of the data. Here, this actually gets a little bit larger. So, just cleaning outliers per se doesn't guarantee that the mean is going to get larger or smaller. That depends on the sign of the outliers. But what you do see is that in all cases, the confidence interval shrinks. So as we clean the data, we remove the outliers, the confidence interval gets smaller. Not surprising, of course, but it's interesting to see. This is quite a change. This decreases by a factor of 3. These only decrease. Oh, here you get a decrease by a factor of 2. So you can, go back and look at the data and see what the values of the outliers were. My guess is here there were some pretty big outliers that were really screwing up the confidence interval estimate. Okay, and then this one, this is a relatively small change. So I guess with weight, with this data variable, there was a couple of outliers, but they probably weren't very extreme. So the impact on the mean and the confidence interval was probably pretty mild.